Hello everybody. Today I'll be talking about chapter 9, which is lecture number 8, about Ampere's law and the magnetic fields. So from your previous knowledge, previous study of physics, you already know that number of sources for getting magnetic field is two sources, either having a DC current, if you have a constant current being passing through certain wire, then you get magnetic fields around it according to right hand rule. So if your thumb is directed toward the direction of the current, then the fingers will be pointing the direction of magnetic fields around it. Also, you can get magnetic fields from permanent magnet. So these are the two sources of getting magnetic fields. But we are talking about static magnetic fields. So in coming lectures or coming chapters, specifically if we talk about chapter number 13, then we will be talking about some other sources indirectly trying to produce the magnetic field by having the time variant electric field. So in chapter 13 we will be talking about Maxwell equations, and you know that in Maxwell equation electromagnetic gathered by having four equations. So if you have electric field, you can get magnetic field from it. If you have magnetic field, you can get electric field from it. Taking into account here and there, sometimes you get density from field intensity and vice versa. For example, in Faraday rule, you will get the electric field intensity from having time variant magnetic flux density, and vice versa for Ampere law. So in this chapter we will be talking about static magnetic fields. We will not be talking about the time variant magnetic fields. It will also treat the behavior of magnetic field strength and magnetic flux density B across the interface of two different materials. So here he talk about chapter 13. Chapter 13 will be discussing boundary conditions also for magnetic field. The treatment uses the static magnetic field as the vehicle or a tool to develop boundary condition, but the result apply to both static and time variant magnetic fields. Okay, so first of all, if we talk about an important formula to calculate the magnetic field, we will be talking about Biot-Savart law. Before talking about Ampere law, we will be talking about Biot-Savart law. So Biot-Savart law, as you can see here, this is the function of Biot-Savart law. So mainly it is calculating differential magnetic field strength, which is the edge, and this will be result from differential current element ideal. Differential current element ideal, as will be seen here in figure number 9.1. So the field varies inversely. This field will be calculated by using Savart law. It is varies inversely with the distance square. So you can see from formula it is related like 1 over r square. And also something very important, that it is not dependent on surrounding media. Unlike previously in chapter 2, for example, there was dependency on the surrounding media by having epsilon r as the denominator of the formula by which we calculate electric field. Unlike here you don't have the dependency on the surrounding media. So and has a direction given by the important thing is how to get its direction, this field to be calculated, how to get its direction. So the direction, as discussed here, given by cross product between both of these terms, between the current element and the unit vector AR. The direction of magnetic field will be decided according to a cross product calculated between the current element and AR. And AR is the unit vector of the vector R. So the relation is, as discussed, will be like that. Now what about R? If you look at figure number 9.1, R could be defined as that vector being directed from the current element, as you can see here, from the current element toward the point of observation. So the point of observation will be around the existence of the current. For example, if you have certain wire, then the point of observation will be somewhere around it. So this is the vector R. Now, depending on whatever discussed so far, so if Savart law depending mainly on the calculation of differential magnetic field, depending on differential current elements. So summation, you can say, summation of all of these current elements will give you the required total magnetic field you're looking for. I.e., in another word, that the summation of all of these current elements will give you a certain integration, and this integration will be closed line integral. Let's talk about example number 1. In example number 1, saying an infinitely long straight filamentary current I along the z-axis in cylindrical coordinate. So this is figure 9.2. By having a point at z equals 0 plane, this will not lose the generality of this point, so it will be an arbitrary point, and this arbitrary point could be defined as shown here, that it is r phi 0. Its location will be r phi 0. Why? Because for any angle and for any radius, okay, and for fixed height to be z equals 0. How to start with the solution of this example? The starting will be sure it will be by constructing the distance or distant vector. So the distant vector will be from any point on z-axis, okay, on that line having this current, toward the chosen point or the selected point to be r phi 0. If we take an arbitrary point on the z-axis, so in this case you are saying that it is on z-axis, meaning its r equals 0. If its r equals 0, then this meaning what? Meaning that you don't have any value for radius, so its value is 0, and for arbitrary phi, its phi also it will be arbitrary, so has been defined to be phi, and for any z, for that reason you can conclude that the location will be 0 phi z. The other point is r phi 0. Now how to construct a certain vector pointing on r phi 0 starting from 0 phi z. This will be by having the differences, okay, like given here. Then you get the required distance vector to be like that. After that, you can also prepare its length. Why? Because in the Biot-Savart law, you will divide on r square, as we previously talking about here. And if you look at whatever you have here, okay, it is italic form, meaning that it is the magnitude of r, not the other form of that vector. So by having all of these things, you can substitute in Biot-Savart law, and substitution will be like that. How you will conclude that IDL to be equal to IDZ? Because if you take a piece of that wire on z-axis, if you take a piece of it, then IDL will be equal to I multiplied with dz, not dx, not dy, but dzy, because it is lying on z-axis. About the direction also will be toward positive z, as assumed here in this figure. So you will figure out that the current element will be IDZ AZ. This to be cross producted by the vector r. So the vector r has been just concluded to be RAR minus Z AZ. And here it is discussed how to get the cross product, so you can review the discussion here, how you can get its cross product as previously done mathematics in previous chapters, so not worthy to be mentioned or declared more and more. And if you have any question concerning to these issues, you can write to me, and I think it is very simple, you can understand it. After doing that, you will get the product. The product will be of this operation of cross product will be RIDZ A phi. So the direction will be decided as A phi. Now you will get back to the formula, okay, the previous formula, and you'll substitute whatever you get in it. And after substitution of all of these things, then it will be ready for taking the integral operation for it. If we talk about the integration, it is very clear that the differential magnetic field here is related with differential height. So you will take the integration just with Z axis. And sure, if you look at whatever you have, you will have some constant terms. All of these constant terms will get out from integration. You can get it here. And the remaining term, okay, you will have dz over r squared plus z squared to certain power, which is 3 by 2. In this case, you don't have the derivative of this bracket up, okay? So you have to follow the method being used previously in problem 2.9, belong to chapter number 2, for getting the result of this integration. The important thing is the limit of integration will be taken here from minus infinity to infinity. Why? Because it is mentioned in the question itself, infinitely long. So you have to take care about the limit to be taken from minus infinity to infinity. By substituting everything and performing the integration, you will get the result to be I over 2 pi r, I over 2 pi r. And the direction, not forget, the direction will be like that. And this will be, this will meet the assumption, the physical assumption of having the direction of current. If you have direction of current to be upwardly, then direction of fingers will be deciding the magnetic field intensity direction. Now it is time to talk about Ampere's law. Previously we discussed Biot-Savart law. So Biot-Savart law is somewhat complicated. And now it is time to talk about Ampere's law. And by using Ampere's law, it is somewhat, if I just remind you, previously in chapter 3, there was a formula by Gauss called Gauss law. So Gauss law is saying Q enclosed, may I zoom it somewhat, equal to closed integral d dot ds. Just for comparison of both of these mathematical equations, you can see that previously in chapter 3 to find the electric flux density D, then the required formula is Gauss law, and Gauss law depending on a certain Gaussian surface, and it is required to take integration all over the surrounding surface area of that surface. So this surface will take a certain amount of charge, as you remember, and this amount of charge will be important in deciding the amount of electric flux density. For that reason, in Gauss, we depend on how much, or we calculate, or we give importance to the amount of Q enclosed, or charge enclosed. Here in Ampere law, somewhat similar to whatever discussed in Gauss law, but in this time will be we will give importance to the current enclosed, I enclosed. Okay, so the formula saying closed integral H dot dl equal to I enclosed. But here you have to ask yourself, enclosed by what? It must be enclosed by a certain path named Ampere path. So as previously in chapter 3 for Gaussian law, we said there was a Gaussian surface. Here also you have something called Ampere path. As previously in Gauss, there was certain conditions to select a Gaussian surface. If I just remind you, first one must be closed, second one sectionally everywhere must be equal, the electric flux density must be equal. I mean sectionally because you may select, for example, a cube, or you may select a cylinder, for example, and maybe sphere. For sphere you don't have any problem, composed of just one single section, but for cylinder, for example, you have top and bottom and surrounding cylinder. For cube you have six edges. So this is what I mean by sectionally. For each section, the amount of electric flux density must be equal. The last condition for Gauss was, if you just remember, that everywhere, all over the surface, electric flux density must be either normal or tangential. So here in Ampere's law, we have something else. You are not talking about surface here, you are talking about path. So this path must be closed. This is the first condition, which type it here, you can see. Now the second one is edge has the same value at all points of the path where edge is tangential. So this is important. Edge has the same value at all points of the path where edge is tangential. Why? Because just like the Gauss law, we have dot product operation. Okay, you can see here. For that reason, for those sections of that path where edge is tangential, then edge has the same value, okay, must be the same value. You cannot take certain section where edge is tangential while the magnetic field is not equal. This will be more understood by taking or having certain example. Okay, so we have example number 3 here. In this example, he say use Ampere's law to obtain edge due to an infinitely long straight filament of current I. Okay, the Biot-Savart law shows that at each point of the circle, okay, in figure 10.2, edge is tangential and of the same magnitude. Example number 3. Use Ampere's law to obtain edge due to an infinitely long straight filament of current I. Okay, so if you apply the formula, you will say closed integral h.dl equal to I enclosed equal to I enclosed. So how much h.dl? How much h.dl? If I just make some discussion here, if you assume this is the line and this is Ampere path and you have a current passing through it which is I, okay, and you have a radius, for example R, then how much will be the total length? How much will be the total length of this path? I mean what? I mean we have this line having this current, okay? So if you assume Ampere path, if you take Ampere path as a ring around this line with a certain radius, sure it is something unspecified, R to be R, okay, for any R. Now, how much will be the circumference? Why I said circumference? Because, you know, it is like a ring, like a circle with certain radius. So, sure, the length of this ring will be the length of its circumference. And we already know that the circumference will be 2 pi r. So by having the integration, okay, so edge is constant. Edge will get out from the integration, will get outside the integration because it is constant, will not be changed. Why? Even physically, if you imagine, according to right hand rule, this is the direction of current, these are the rings of magnetic field intensity. So having certain distance, same distance for each point of this ring, okay, then you get same amount of magnetic field around it. So edge will be independent on R, for example, or phi, or height. For that reason, it will be constant and will get out. If get out, you will get out just the magnitude of it. Why? Because you know mathematically you have dot product here, so you cannot get out the vector of edge outside, but it will be magnitude of edge. For that reason, it is typed here as italic form, meaning that it is the magnitude of edge. Now, magnitude of edge multiplied by the length of circumference 2 pi r equal to the I enclosed. How much I enclosed? Sure, I enclosed will be I. And if you examine the solution here and to be compared with whatever previously in example number 2, example number 2 done, okay? In that example, if I just get back to the previous, it was example number 1, okay? So just like in example 1, okay, we follow complicated steps until getting the required result. Unlike here by using Ampere law. So just I'm sorry about numbers. Actually, this is example number 2, and the other one example number 3. Okay, so keep in your mind to change these numbers. Actually, I changed the order of these examples. Why? Because in the reference, this example, which I'm solving now, is discussed before talking about Ampere law, and it is already application for Ampere law. For that reason, there was certain postponing and preponing, and has been fixed. So by having the application of Ampere law, you will get the result to be found out just by a single step. By a single step, you will substitute just the circumference, and you get whatever you're looking for. Again, there is a problem in using Ampere law, that you have to know that the direction will not be specified. So previously, you must have an idea about what will be the direction of magnetic field. Why? Because it is a calculation indirectly calculated by having the integration of edge with dl. So as in Gauss law, previously in Gauss law, there was a problem of direction. Direction could not be specified according to mathematical calculation, and totally it was depended on guess. So you have to guess what will be the direction, and here it will not be a big deal. Why? Because you will be depending on right-hand rule for deciding the direction, as will be discussed in next example also. So for next example, in this example, you have an infinite current sheet line lies in the z equals 0 plane with k equal unknown. It is just k ay, as shown in figure 9.3. Find edge. So in this example, I'll just remind you about k. You remember from your previous study in chapter 6 that k is the current sheet density. K is current sheet density. So how to be solved? How to solve this example or such example? You have current sheet density, unlike having a certain line with a certain current. Previously, we selected a ring, okay, to be ampere path, but here, what will be the ampere path? Ampere path, if you think about ring will not be applicable, but rectangular will be more applicable. Why rectangular will be applicable? If you look at the rectangular shape, so you have two conditions, just if we review it. First of all, must be closed, it is closed. Second thing, whenever you have magnetic field tangential with sections of this line, then the amount of magnetic field must be equal. So if I just zoom it, okay, and imagine whatever you have, you will have certain rings or you will have certain loops or rings representing the magnetic field around each of these plotted line. Okay, so these are the magnetic field if we plot it like that. Now all of these together, all of these rings together will be unified to produce certain magnetic field lines like that. You can see here. Okay, so if you talk about this piece of line, then what? Then imagine how much will be the amount of magnetic field. Sure, magnetic field will be equal all over these sections. For the other side, under the current sheet, also from section 3 to 4, it will be the same phenomena. The amount of magnetic field will be equal. So getting back to Ampere law, we haven't applied it yet. May I type it here? So this is H dot dl equal to I enclosed. Now, if you think about this side of the equation, how many sections you have? You have 4 sections, but fortunately you will not calculate the amount of H dot dl for all of these sections. Why? Because somewhere, for example, may I zoom it? For this section, for example, okay, and this section, I mean the vertical sections, okay, from 2 to 3 and 4 to 1, the amount of dot product between H dot dl will be 0, and it is very obvious that you have right angle. For that reason, you will get 0. So we will expect that you will have a result just for the sections from 1 to 2 and 3 to 4. For that reason, it has been solved like given here. H dot dl equal to H times 2a. Why 2a? Because the length of the line is 2a. If you just get back to the dimensions, okay, the length of from 1 to 2, for example, it is 2a. So H dot H times 2a plus 0 plus H times 2a from 4 to 1 plus 0 plus 0. So you have 2 0, you have 2 non-zero terms. Equal to, on other side, you have k multiplied with 2a. From where you get this? From having the given current sheet density. You are given current sheet density in the question to be k equal to k ay. For that reason, when you multiply this amount of current sheet density, which is in unit of ampere per meters, for that reason, when you multiply with meters, meter will go with meter, then you get just the ampere value. So how much is the amount of current enclosed inside here? May I just erase all of these to discuss this particular thing? Okay, imagine these lines representing the amount of current passing through this square ampere path. So how much is the required length to be multiplied with it? It is 2a. For that reason, 2a will be multiplied by the amount of current sheet density to get whatever we're looking for. So as a result, you can see here that you have on this side you have 4a, on this side you have 2a, so a will go with a and 2 will go with 4, and you will get 2 on this side. You get 2h equal to k. For that reason, h will be equal to k over 2. Okay, so to generalize the derivation taking place here, you can say that h will be equal to 1 over 2 for k cross product with a normal. This is very important formula, has been derived. Why? Because depending on the current sheet density and the normal to this current sheet density, by having the cross product between them, you will decide the direction of magnetic field. For this example, if we just get back to whatever we discussed here, previously we said that here you will have rings like that, so all of these rings will be together, will be forming the direction for what? For the magnetic field intensity. So what will be the direction of magnetic field intensity? Direction will be AX. For that reason, as typed here, maybe not very clear. Okay, it is as we said, k over 2 AX, k over 2 AX. Now, section number 9.4, relation of J and H. J, previously we have been talking about J as a current density in chapter number 6, and its unit is ampere per meter square. It's unlike previously in previous example we're talking about K. It's unlike K. K is current sheet density, while J is current density. So current sheet density is the current density per unit meter, while this is the current density for surface area, for example. So the previous formula of ampere law we're talking about, it was the integral form. Now the same integral form could be written in mathematics in another form, in differential form. So in differential form, if you write down the Ampere law, it will be given like that. I can say here that this is also Ampere law, but in differential form. So curl of H equal to J. And J here, it is conduction current density, but will not be discussed in this chapter. In coming chapters, maybe in chapter 13, will be discussed more that there is two types of current density, the conduction current density and the displacement current density. For now, it is JC, okay, as much as not type it as JC, but will be in coming lecture. This is one of Maxwell equations for static field, and as type it here, if H is known throughout a region, then curl of H will produce J for that region. Now, mathematically, you will be facing certain difficulties according to whatever you have and which coordinate system you have. For example, if you have Cartesian coordinate system, you have to follow this equation, or taking the determinant. It will be much more easier taking the determinant of having the differential vector, partial differential vector with the vector of H. Here generally he's talking about A, but A will be used as edge if you apply it for Ampere law. For cylindrical coordinate also you can take this determinant to get the result, and for spherical it will be somewhat more complicated. Okay, you have to follow this equation. You have an example. Example number 4, a long straight conductor cross section with radius A has magnetic field, strength H within the conductor R less than A and H equal to this value for R more than A. Find J in both regions. So may I zoom it somewhat like that, okay, just to get an empty space. If you assume that you have a certain conductor to be like that, okay, so this is A, radius equal to A. Now either being typed like that, or just like given to us like that, okay, as a small letter, okay, italic small letter. So within the conductor and outside the conductor. Outside meaning on surrounding the conductor. Okay, so you have two values. This one for this region and this one for these regions around the conductor or outside the conductor. Now the important thing is to know what is required, what is asked from me The asked thing is to find J. So you have to calculate J. J will be calculated according to Ampere's law, but differential form Ampere's law, not integral form. J equal curl of H. So which coordinate system will be used? Which one is more suitable here? Because we have a straight conductor cross section with radius of A. So sure it is like a cylinder. For that reason, cylindrical coordinate will be used. And if you apply the previous rules or previous formulas, for example, this will be used, then you will get this result. This result will be for inside conductor, and for outside conductor you get nothing, you get 0. And why? Why you get nothing for outside conductor? Sure, you get nothing. Why? Because the current will be confined within the conductor. Outside the conductor, you will not have any existence of the current. For that reason, physically, it seems logic, because you don't have existence for current outside the conductor. And mathematically also has been proven here that it will be equal to 0. I think last section in this, no, we have 2 sections remaining. So another section talking about the magnetic flux density. Just like talking about electric flux density previously in chapter 3, here in magnetism also you have you have magnetic field intensity and magnetic flux density. The magnetic flux density will be called B. Here will be called B, okay? And B will be in units of Tesla. In units of Tesla. B is given by this formula to be mu H, where mu is permeability. If I just make analogy between them, in electricity you have D equal to epsilon E, okay? Both are vectors, and also here both are vectors. So as previously talking about, permeability will be just like permittivity. Permittivity, as previously we talking about, for air it will be intrinsic permittivity or epsilon naught, okay? For any other material it will be epsilon naught multiplied with epsilon r of that material. Here also for permeability you will have mu naught for air permeability and mu naught times mu r for any other materials. So in electricity there was another thing also, in addition to electric flux density and electric field intensity, okay, as we're talking about here, okay, there was something called, it was like that, it was a psi, if you remember, okay. What was the meaning of psi? Psi, it was the electric flux, and psi, we said electric flux equal to same as the charge Q, So here you will have magnetic flux also, just like electric flux previously talking about, okay? You'll have magnetic flux. So the magnetic flux will be called phi, and this phi could be calculated like that. And also I can remind you about Gauss law, when Gauss law saying that psi equal to Q enclosed. May I zoom it somewhat to be able to type it well? Equal to closed integral d dot ds. d dot ds. Okay, so making analogy between them, you can find that the flux equal to the density multiplied or dot product with ds. Also here the flux equal to the density dot product with ds, and closed integral being used, and here even if it is not typed as closed integral, but also same meaning, that integral will be performed all over the surface. You have example here. In this example, saying that you have this structure. You have like a window being defined with certain radius and height. So find or calculate the flux crossing this portion or of this window of a plane having a certain phi equal pi over 4, okay, and defined with r and defined in z as plotted in this figure. Keep in your mind that you have a current of 2.5 amperes along the z-axis, okay, in the az direction. Now applying the previous formula, this formula which we're talking about, okay, applying it, which is saying phi equal to b dot ds. Now the important thing is to know what's given to me. I have to find the flux. So flux will be calculated like so. If I make just discussion, okay, b dot ds, all over the surface area, okay. So I don't have this, but I can calculate it from saying b equal to mu naught mu r if you have, okay, multiplied with h, and if nothing mentioned about material, then you can just take this as unity as well, okay. So from h I can calculate b, then I'll substitute it here up and calculate the magnetic flux, but h is not given to me. Also I have to calculate it. Fortunately h is very simple. Why? Because already previously it has been calculated for such case to be like that, Why? Because it is the case of having a wire and you have a certain current in it, then the magnetic field will be like rings around it. So just you have to substitute these values in it to calculate whatever required from you. The important thing also to know that how much ds will be equal to dr dz a phi. Why? Because if you examine the given figure, if you take a small window here, okay, so this is dr and this is dz, because this is differential height. Now taking this with certain direction, okay, so sure direction will be a phi, okay. So by having ds and its direction will be multiplied with b with its direction, then you have to make the integration. Integration sure will be performed for both of these, for dr and dz. For dr, it is given to be from 0 to 2, and also for z it is from 0.01 to 0.05. Then you have to take the integration, and the closed number result will be found out. Okay. Something very important, mathematically maybe and physically, will be discussed here, which is about something called, it should be, as you can see here, it should be observed that the lines of magnetic flux phi are closed curves. Okay, this is in contrast with electric flux phi. Okay, yeah. Let's first talk about its mathematics, then we will discuss it physically. Mathematically, if you take del of B, it will give you 0. Del of B give you 0. May I write down here del of D? I know it is too early, maybe discussed in coming lecture, in coming chapter, but no problem if just for making analogy between electricity and magnetism. So if you take del of D, okay, will give you rho, and rho is, you know, charge density. So this meaning what? Meaning that in electricity, now I get up, I get finished with mathematics. Okay, I'll go to physics to discuss it. Okay, this is whatever taking place in electricity, okay, and this is for magnetism. In electricity, and as discussed in chapter 2 and chapter 3, for getting electric field or electric flux, you must have source and destination. You must have starting point and ending point. While here in magnetism, you will not have any starting point. For example, the North Pole and South Pole for our planet, okay? When you talk about Earth and you have South and North Pole, you have certain different points, okay, and you will have a rings, okay, a certain ring representing the magnetic. If you talk about our planet Earth, okay, and you have axis here, now this is the North Pole, this is South Pole, then you will get the lines of natural magnetism, okay? So these lines has no start, no end points. These lines will be circulating between north and south without having starting and end point. Unlike previously, when we talk about charges, then you will have certain, for example, charge, this is observation point, okay? You will have a start for that electric field. So electric field unlike magnetic field in that matter. Another example also for magnetic field, when you have certain wire having certain current, then if you imagine the rings of magnetic as according to right hand rule, then sure the direction will be like that. Okay, so these rings will be like a complete ring and will not have a starting and ending point. And this is the physical reason of having zero here for the formula of taking del operation for B, which is the magnetic flux density. Another section is about vector magnetic potential. Maybe this vector or this term physically not having a very sensible meaning, unlike having potential in electricity. You will directly think about the potential difference, which is the voltage, but here you will have it, okay, just as analogy between electricity and magnetism, but also as a calculation will be benefit in calculating of magnetic field intensity, as will be discussed more in coming year in talking about antennas, for example. Vector magnetic potential will be used more and more. So previously we have been talking about the potential difference and the relation between potential difference or voltage and electric field intensity will be controlled by having this equation, E equal to minus gradient of V. Here we have this equation by which we can calculate the vector magnetic potential by taking the curl of A equal to B. Where B is the magnetic flux density. And also an additional formula saying that del of A equal to 0. The vector magnetic potential A can be determined from the known currents in the region of interest. Now it is time to talk about boundary relations for magnetic fields, which is last section. So in this section, consider an open surface S whose boundary is a closed curve C. Stokes' theorem states that the integral of the tangential component of a vector field F around C is equal to the integral of the normal component of curl F over S. Or you can say it follows this formula. If F is chosen to be the vector magnetic potential A. Okay, so this in general, mathematically, according to Stokes' theorem. Okay, he said here Now, according to this, okay, if F is taken to be vector magnetic potential, so Stokes theorem will give us this equation. And already we have been talking about this previously in previous section, and even we solved certain example on it. Just I remind you, this example, we solve it, okay? And for first time it was discussed here in this section, okay? So that's all for today, for this lecture, by which we have completed chapter number 9, and for next lecture we'll be talking about or we will start with solve the problem of this chapter. Okay, see you.